the organizer for giving me this opportunity to present this talk. And what do we do? I mean, in contrast to the previous talk, is something very elementary. And since the previous speaker already talked about what is a complex fluid, I don't think I have to dwell too much on that. And so here's the summary of my talk. What is the kinetic basis for the visco-elastic type of fluids? And I also want to say a few words about the Lattice Boltzmann equation in case, I assume not too many people are expert in this area. And finally, I'll show some very elementary preliminary results. Okay. So first part is what is the Lattice Boltzmann equation for, let's say, simple fluids, hydrodynamics. Let's get that right first. We start with Boltzmann equation, as opposed to Navier-Stokes equations. And the route from kinetic equation to hydrodynamic equation, it's well understood. All right? And so here we are not trying to talk about that. We simply want to construct numerical schemes to solve hydrodynamic equations. So here's the Boltzmann equation. Now, in order not to waste computational time on the collision term, you do the linearized one. And the simplest one I use as an example is what is called a BGK relaxation model. It's a linearized model. As far as the kinetic equation is concerned, the equilibrium is the Maxwellian. The hydrodynamic moments we are interested in, or conserved moments, are density, momentum, and energy. And these are the quantities the equation of these are the hydrodynamic equations. And so, if we use the BGK equation, we can pretend, this is the ODE, integrate along characteristics, and that's what gives you this solution in general. Now, based on this solution, you can construct either schemes for incompressible flow or compressible flow. And I only want to concentrate on incompressible flow. And that's Lattice Boltzmann scheme. Now, you can do Taylor expansion of this delta T up to the first order, and you get this equation. Very simple, Euler type of scheme. So, the time is discretized. Now, what remains to be discretized is the configuration space and the velocity space. Now, if you want to solve hydrodynamic equation and you solve it in the phase space of kinetic equations, you're bound to lose because of the dimensional parity. And so you must reduce the momentum space drastically. And let me show you how we do that. So there are 3 steps. Number 1, for the incompressible flow, you want to do the low Mach number expansion. Then you want to discretize the velocity space with only the necessary and minimum number of velocities. And then you will discretize the configurational space according to what you have here. So it's a very specialized discretization which you ever described. Well, first of all, low velocity expansion. You just do the Taylor expansion. All you need is expand up to the u square. Okay? The reason for that is in your momentum equation in Navier-Stokes, you have u dot grad u. It's a u square term. That's all you need. If you eliminate these 2 terms in this expansion, you will get the Stokes equation. Okay? Then similarly, you can expand non-equilibrium distribution in terms of grads or what other expansions. Now, this A, this coefficient, could be hydrodynamic variable and their derivatives. Okay? YH, this is only the function of the molecular velocities. So this is the basic expansion. And all you need to do is up to the 2nd order. So it's a very simple expansion. Now, since we're computing the moments of the velocity distribution function, and we discretize the velocity space, and so the moments calculation becomes a quadrature, those integrations. And we must demand the integration and this quadrature must be equal up to certain order for certain moments, for all the hydrodynamic moments as well as their fluxes. And therefore, if you are concerning mass, momentum, and energy, their fluxes are momentum, heat flux, okay? And so the highest order moment is the third order moments of the distribution function. Now, if you remember that we have this Maxwellian or Gaussian type of weight, it naturally leads to the Gaussian quadrature for velocity space, okay? And in order to give a concrete example, I will choose two-dimensional space. And in two-dimensional space, I also need to choose what coordinate system to use. And let's say we use Cartesian coordinate system. If you have Cartesian system, then the moment evaluation boils down to compute the moments of this monomial. And computation of this monomial, the moment of it, becomes product of two integrals in one dimension, thanks to the feature of the Gaussian, because it can be decomposed in Cartesian setting. Okay? Now, therefore, your two-dimensional integration or quadrature, it's been cast into the product of two one-dimensional one. And bear in mind that now we're still dealing with this Gaussian type of quadrature. And so, as I said, we need third order moment to be accurate if you want conservation laws. All right? And so now, for this 1D quadrature, we know that we have 3 points. We got fifth order moments correct. So that's more than enough. So you can do these algebraic manipulation. It's just renormalization. You have this theta, rho RT type of thing, and then you want to renormalize it. That's all it is. And so what happened is that you have 1D, you have 3 points, and then in 2D, it's a tensor product that leads to 9 points in velocity space. Okay, so in order to guarantee the hydrodynamic moments as well as their fluxes to be calculated accurately by quadratures, 9 points is enough if I choose the Cartesian coordinate system. If I choose the polar coordinates, the discretization is triangular lattice as opposed to square lattice. And so you have to have this 6 equal side of the circle, basically. So what I have demonstrated now is that velocity space can be discretized into very, very few points only in 2D. And you can do the similar thing in 3D. Okay, in 3D, you have a cube. You have middle point, you have 6 faces, 8 corners plus 12 edges. And we can show that in order to get all those moments correctly, you at least need 13 points. That is 6 faces plus, it's the 12 edges plus the middle point. That's the minimum requirement. And then in combination, you get 15 points or 19 points or all of them. Based on this discretization, it will be 27 points, a full set. All right? So this is 2D model. And so if you have that discretized velocity in velocity space, then the discretization of the configurational space is trivial. All you need to find is that the grid spacing is equal to all those velocities multiplied by your time steps, such that all the discrete velocities at one time step is only hopping from one point to the next last point. So you basically have a grid. At each point you have 9 velocities. One is 0 velocities, always sits there. And the other 8 velocities just going out in one time step in the nearby points. That's the picture. So in equation, this is it. I'm using this Boltzmann vector notation for all nine distribution functions. And so before that vex, it has a collision. So how do we do collision? As I said, I use the BGK model for the derivation. It's just a simple example. But what I do usually in simulation is not BGK model. What we do is called multiple relaxation model, and which correspond in kinetic theory Gross-Jackson model. You have finite or infinite many eigenvalues you can choose. Okay, so in Lattice Boltzmann, you can show, this is easy to be shown, that you have q velocities. You can linear map into q moments, and this is a unique linear mapping. You just compute those moments, and there is only 9 of them, or whatever number of them, independent ones. It's a simple linear algebra. Those moments has physical significance. First few of them are the hydrodynamic variables, and they are higher order moments, such as stresses and the heat fluxes and high order moments. The relaxation time of these non-conserved moments are related to the transport coefficients. So the picture is very clear from the kinetic theory. The equilibrium moments, of course, they don't relax. That's why they are conserved. Only the non-conserved moments relax, okay? And their equilibrium are the functions of conserved ones. So these are basic kinetic theory, okay? And so what you do is that besides rho, or I call it delta rho, and J, which is rho U, these are conserved moments. The other 6, let's say you have 9 velocities, the other 6 moments are non-conserved moments if I don't consider energy conservation. And these modes are, well, this is energy type of modes. And there is energy square type of modes, it's force order moments. And there are heat fluxes, and there are 2 stress type. Okay? So the relaxation of these 2 modes related to the shear viscosity. The relaxation of this guy related to the bulk viscosity. Okay? And then relaxation of these related to heat conductivity if you have the energy conservation. The picture is very clear, and the implementation is very trivial. Okay? One of the popularity of this kind of model is that you go out the street anywhere. You pick any guy, said, okay, can you come in, write a Lattice Boltzmann code? Yes. Better than 50% probability, you will get it. Okay? That's the advantage of that. Whether they can do the right thing or not, it's not sure. All right? So in what follows, I will show you how to do the similar, full types of model, foolproof model for visco-elastic type of. And here, I write down that transformation here. Okay, and to do this, it's straightforward. But the first one, why you got 1, 1, 1, 1, 1? Because it's power 0 of all those velocities. We're talking about moments. Then you have a x of velocity x component, power 1. And here's x, y component, power 1, so on and so forth. All right, and so this, when you write down all these moments, and then you use the Gram-Schmidt orthogonalization procedure to make it all orthogonal. So this matrix, each row of them are mutually orthogonal. All right? And so the inverse of it is just to transpose it multiplied by a diagonal matrix, which are the norms of these vectors. That's it. The inverse of this, the calculation is absolutely straightforward. There was no complication whatsoever. Okay, so from that, you can derive, we are solving this set of equation. Okay? And here's the stress. Okay? And then you have these transport coefficients. If you use the single relaxation time, what happens is that you only have one relaxation. And often what leads to two problems. One is numerical instability, and second, incorrect boundary conditions. And I will leave it at that.
So how well can you do incompressibility? You had a
Okay.
You had a little tilt. You had a
Here,
there.
yes, it depends on the order of accuracy. This is the second order scheme, so that I purposely say this. It's a second order in delta x.
So as accurate as you like, if you make the time scale short enough? Or
Pardon?
you mean that becomes as accurate as you want if you... Do you have a controllable discretization?
Yes, if you have
So
more velocities,
Yeah, exactly.
you will have higher order spatial discretization, but the time is not an independent.
Yes.
dx dt is related by what is called a diffusive scaling. This is well known in kinetic theory.
But in practice, the compressibility is controlled by the Mach number, right?
No, not really.
Okay.
Mach number is a CFL number in this context.
Mhm.
You can prove that.
Mhm.
Okay, so now, complex fluids. People in kinetic theory like to use Smolensky kinetic equation to do complex fluids, okay? So this equation deals with the distribution function of this directory, M, on a unit speed, okay? And you have a set of equations which will make you headache. Now, there are various potential you can use. And depending on what potential you use, you derive this monster. The stress due to that M, okay? They call it nematic stress. So, what I do is that numerically, you have kinetic equation, you solve it in space of M, okay, and X, of course. Then you compute the moments of this, and then you construct this stress. This then coupled to the velocity field, and the velocity field come back, affect the F. So you basically solving the kinetic equation and the four set of incompressible Navier-Stokes equations separately but coupled. You can see how horrendous this scheme is. And what I'm trying to do here is trying to cheat, not to do this. Okay, do it simple. Simple. So how do we do? Well, again, we go back to the kinetic equation we love with linear collision term, and we introduce some internal degrees of freedom. Basically, exactly, is that M. How do we do that M? Okay? And so, now, you think about it. What we can simulate is that M, on the unit speed, that was the distribution function of it. And the distortion, angular distortion of that is what's simulated by Smolensky equations. And depending on how accurate you discretize that, you compute the moments of that equation. If we want to just do the low order ones, what do we do? Well, still the same thing, but now you want to include in 2D, let's say. Before, if I do hydrodynamics, I need 9 velocities in 2D, right? I will include 2 more degrees of freedom to describe a tensor, because traceless tensor in 2D. Okay, that's the degrees of freedom. That's that bracket MM is. So that can be embedded into Lattice Boltzmann equation. Okay, so basically what you are doing is that you're trying to mimic that traceless tensor and couple with your velocity. The coupling is through the equilibrium. So here is the model. You still do the same. The only thing different from the hydrodynamic model is that I have 2 more degrees of freedom. You see, I have 3 distribution functions correspond to 0 velocities. One of them is really in the momentum space, but the other 2 is carry those 2 numbers, which are traceless tensor in 2D. Okay? Just 2 numbers.
Can you backtrack a little bit? You had the new degree of freedom theta, right?
That's right.
You want that to be related to M somehow.
That's M, yes. And the M, the key is that I don't want to simulate M. I want to simulate the moments of M. So if you take the second order moments of M,
Right.
that becomes 2 numbers. and two numbers are encoded in these two numbers. That's it. That's my manipulation, my cheat, or my way of cheating. Okay? Now, you can have a higher order moments, then I have to encode it, a tensorial structure, into that. So, these are the equilibriums. You can see that these two are coupled to the conserved ones. Okay, this is always like that. And how they couple, it depending on the symmetry. Okay, these are just details what those vectors look like. Okay, but then let's look at the equation. It came out. You remember that I have this. Okay, this is the mass conservation, right? This is the momentum conservation equation. If I don't have the 2 extra 1, you can forget about this. And here is just another, this term will be gone. Okay? But now I have 2 more bit among these 2 numbers. So I have this. With all these numbers which I can tune. So this is related to the Jeffreys model. I think you're familiar with that. So I can get linear visco-elastic model done this way. Now, deriving the equation is relatively easy.
Sorry, can you go back to the next slide?
So the P is the two-dimensional kind of capital P.
Yes. You see, you have, it's 0 at diagonal moment, right? It's 0 at diagonals. It's just off diagonal, you have these 2 numbers. That's it. It's traceless. It's 4x4 thing, and then you only have 2 elements, non-zero ones. These are just transport coefficient type of thing, The construction of the model is very simple. Writing a code is very easy. The effort usually is the numerical analysis, ensuring the truncation term, is consistent, it will converge, blah, blah, blah. Okay? So here is the Jeffrey type of model. You can construct similar model like Maxwell and other models through this same thing. Okay? So this is one type of, I call it model 1. Okay, and I'm not going to do too much with it today. I'll do the second thing. So you get the picture. By introducing additional degrees of freedom in a higher order moment, which relate to your internal degrees of freedom, I can construct sort of linear and nonlinear viscoelastic models. Now, the second thing we wanted to do is this. Suppose we want to simulate some viscoelastic fluid phenomena. One thing we can observe is that usually it deals to some very, very long relaxation time, as the first speaker introduced, of those large molecules, so on and so forth. So in the viscoelastic fluid, there are some quasi-conserved modes with long-lasting relaxation time. So can we mimic this? All right? So with this idea in mind, so what we can do? We have stresses, right? So if our stresses, it's no longer relaxed in fast way, like square separation, we introduce a longer time to allow the stress to relax very long, or even conserve what will happen. Okay, and so this is what we are going to do. So now, but in order to do that, your numerical scheme has to be stable and also consistent and so on and so forth, all right? So you cannot just use 9 velocity model. 9 velocity model allow you to do hydrodynamics because of scale separation. The stresses only need to relax fast to produce the viscous effects. There's nothing else they do. But here you need more. So what happened is that here the first few bits are the original 9 bits. Then you include 4 more velocity degree of freedom, or 4 degrees of freedoms. Now you introduce a stress type, okay, moment, just like this, I use capital, but there is 2 vector, and there is a, this is a 4th order, this is a 6th order type of, it's useless, but you need those degrees of freedom, okay? So what we do with it? Well, so that's one model. The other model is what I call the shear thinning and thickening. And this is also very popularly used because you can analyze the model by using what is the asymptotic expansion. And you can find that all these stresses, these derivatives are readily available in Lattice Boltzmann calculations. So what you can do is make your viscosity depending on the stresses to do a shear thinning or shear thickening. So I illustrate 3 models. Okay, the first one, you introduce degrees of freedom such that you mimic the 2nd order moments of the directive. The second one, you allow the fluid's stresses to be quasi-conserved modes, meaning they have very long relaxation time. Okay? Or even conserved. And the third one, you simply just use the hydrodynamic model but make the viscosity depending on the local shear rate.
By changing the relaxation time. Or
By
changing the relaxation time in the...
No, you just make that equal to that. You compute. That's all local information. All these information are local. You just need to compute it.
How do you make the viscosity dependent on the shear? You change the relaxation time?
Yeah, because it's a function of that. Exactly. So tau is a function of that. Period. I mean, it's just linear function of it. Okay, or power law. Whatever you like, because it's local information. When you compute those moments, you have this. Okay? So I described 3 models. The first model, we have done some tests in the waves and all that. So we already studied extensively. So I'm not going to talk about it. Today I'm just going to show you some basic results of using the 2nd and 3rd model to mimic this phenomenon. I mean, if you have a shampoo, all right, and then the air bubble is inside, when it comes rising, it will have that long tail. Can we reproduce this phenomenon? That's all we want to do. Okay? Very simple phenomenon. So here's an experimental picture. This is just an air bubble in oil, Newtonian fluid. And this is non-Newtonian. And depending on the shear thinning, factor they put in some additives, the bubble radius will change. Okay, that's what they do. But all we want to do is this. See, we can do that. And now I must apologize that the visualization is really poor because we just did this, and then after my collaborator sent me the picture, and I said, hey, can you do something else? He's gone fishing already. So now, okay, so you have an air bubble coming up. This is a Newtonian fluid. So you know what will happen. It's just to give you a rough idea. Okay? Air bubble comes up and it will have this cap. Okay? It's like a mushroom.
Does that reach nearly steady state by the end of that?
Oh, by the end, it was just maintaining this.
It's just
Yeah,
about
yes,
steady state.
yes. So that's what happens.
Yeah.
Okay, so
So how is the free interface included by the free interface?
oh, okay. I didn't dwell too much on that. The way we do free interface is by level set. By level set. By level set, you basically have this equation. Okay? Whether it's equal to 0 or not, depending on, number 1, this is a distant function or not. Number 2, is this the true velocity of the interface or not? So you make some approximation. Okay? To do this, I only need one conserved variable, a scalar. So I use y velocity, very trivial. I don't even mean okay. So you have another set of equations. Just do
So
this.
you add additional
Yeah,
three items.
that's right. Just do this, purely for visualization purpose.
But you have different viscosity, so you have two different viscosity.
Yes, that's
Phi
right.
dependent, yeah.
Huh?
Dependent on the phi.
No, it does not. It's just you enclose. Let's say you originally initialize a bubble which is a circle. Inside is through A, outside is through the B, and you can specify its property.
Does it have an interfacial tension or not?
We don't do that yet. Here we don't do that yet. This is very preliminary demonstration. Okay, you can install. There are two ways to do interfacial. Yeah, yes, you can do it, but here the key is not to. So that's one thing. Okay, so it's Newtonian. You can see that coming up, and there is a bottom is cave in. All right.
So the surface actually grows
Mhm.
with time. It gets bigger, the droplet, is it?
No, it does not.
It doesn't.
But that's why I said the visualization. He used the color scheme, which is a very bad idea. What ought to be done is just psi equal to 0 and black and white. Then will be no issue. Okay. Well, so this is a shear thickening. So shear thickening one get wrong thing. You see, there is a point at the top. Okay, so it's definitely wrong. You cannot. All it means you cannot use that simple-minded model to do this phenomena. Okay. Why?
Your LBM just gives you a shear thickening viscosity, right?
That's right.
Then why did things go wrong? If I do a shear thickening viscosity calculation, I wouldn't get the tip.
You won't get this.
I should not expect this pointed top.
Well, depending on, I guess, how you specify that function and so on and so forth. Okay, so we do something very simple, just linear power. This is just one choice. When you do the shear thinning, there are so many choices of that function. I just make a simple choice. Okay, I just demonstrate that I don't, because I don't know how to choose that. You can say that. All right, but then if I do this, the last one, you can see that tail grows to give you that tail.
So this is shear thinning fluid?
No, this is not shear thinning. This is the one with the quasi-conserved mode. Okay, so what does that? I have a bubble. Inside, the viscosity is much, much smaller than the outside one. Okay, and the outside one, which you have those extra mode, those P or whatever, which relax very slowly. So that's what leads to this.
But, okay, you say it's non-Newtonian, but
Yes,
then you clicked on.
yes.
So
Actually, I should put quote.
is it not shear thinning?
It is.
If you were to construct the
No, it
constituent
it is
relation
not.
that emerges.
no, it is not.
And what is the color? What calls the color?
What is the color? Just plot the color of that phi.
Why would it
So why?
shrink?
Why, but it should,
Well, because you see-
it's not conserved here.
Okay,
If the color is fine.
okay. If this is exactly equal to 0, it is conserved. But if you do it too crudely, depending on how you do this, right? How do you compute interface velocity? I don't do Riemann solver, you see. So I made very crude approximation in this. When I do that interface velocity calculation, I can do some iterative scheme to make sure this is indeed interface velocity, but the calculation will be much more expensive. So I make some sacrifice.
So it sort of dissolves in the blue, right?
So what happened? Let me tell you what happened is, you have a phase field, let's say, okay? You take a cut. There's a finite thickness of this. When you initialize, it's very thin. When it goes to steady one, it goes to its steady state, let's say about 5 grid spacings. If you constantly adjust your color scheme, you won't see this. That's why I said if we use the black and white, you won't see this. We can cheat.
Yeah, but if you interpret it physically, it would
Mhm.
be that internal fluid
Hmm?
dissolves in the external
Well,
fluid.
it does not completely dissolve. You see,
Partly,
That's not-
don't
that's
say
not enough
completely.
it will not dissolve, it will not completely dissolve because there are some mechanisms for it to go back here. But when you initialize it, okay, the other thing we could do is this. When you initialize it, you can iterate it such that to make it a steady profile, okay, with this, and then you see much less of this. This is numerical artifacts.
This now numerical question. Do you compute all this big, also all this big region, this blue?
Oh, we do. We do.
Can you do something to save computation?
I don't know how to do that. Well, I mean, you can do great refinement. That would be one way of saying it. Meaning that, okay, yep, actually, okay, you see, then you cannot ask a street guy coming to do it. You cannot. So what you do is you do the Lagrangian. You do Lagrangian. We actually do this for other type, not for this one. You have a Lagrangian, markers on the interface. You do local grid refinement, coarse grid outside, only fine grid round boundary. You can do that. Then you will completely get rid of those effects.
Can I see this as sort of a numerical diffusion, just from the level set equation?
Yes.
Because you
Think
said
you
it's
can,
not
yeah.
well preserved, yeah? So that's what you
It's
see.
okay. The mass is conserved. Okay, but you see,
It's just confusing.
Yes.
yes, it's just that it's not. It's getting out. If what we ought to do is when we initialize this, iterate, fix that position, iterate it such that the profile is what it ought to be. Then let it go. Then you won't see this.
This is contour dynamics, so you care about the contour, so therefore you care about the gradient of phi, and that you need to resolve accurately in order to
Mhm.
track the thing accurately.
When you say this one, this
So-
time,
Exactly. You need to know that the gradient of phi along the evolution doesn't deteriorate, because that's
for
what
this.
makes the transition from your 1 and 0 essentially what you're trying to.
So for this one, actually, we can show that for this scheme, we can have second order, but it's calculation of this.
No, that wouldn't diffuse, but never mind.
Okay.
What fixes the width of the interface here?
What's fixed? Okay. You can put in some sort of particle-particle interactions between them. Okay? Let's say you have A and B. And then depending on whether they like each other or don't like each other, they will see each other, the local gradient, and they will turn the other way or, diffuse. So that's what it is.
Yeah, and this you do here.
Yes,
Mhm.
very primitive.
Coming back to the physics a little, so this is your second model, right? This is not the Jeffrey model.
This is not Jeffrey model.
So there is extra long relaxation time.
That's right.
On top of the visco-elastic relaxation time that's already in your.
No. You only have, you have a Navier-Stokes equation. You have regular Navier, plus you have some stress type of terms, which relax very slowly. And the inside, you don't have that.
Yeah, I think Peter asked this question already. How can we think of the constitutive equation as?
Well, I haven't derived the constitutive relation. We could sit down to derive that. We're just trying to see, how do we, do this type of simulation easily, so to speak, to duplicate that kind of phenomenon. Now, there are better ways, of course, of capturing this kind of thing, and here I'm going to just show one of the examples. You don't use visco-elastic. What you do is that you use free surface, you use something very viscous, and to simulate forms. So this is like a bread making process. You have a fluid, and locally you give something which gas produce gas, yes, all right, and see how they deform, become the bubble form. So if we use this kind of capturing scheme, I mean, we can produce very sharp images. There are various, I mean, ways to do the interface capture. That's the key. And this is not done by us. This is done by a group in Germany. Yes, question?
No.
Okay.
Just say that this beautiful artistic image.
Exactly. So we can do the same for the bubble. To render very sharp, the key is that tail. Our purpose is only trying to reproduce that tail. In fact, I mean, the effort to reproduce, I mean, to do the graphics is way more than the simulation itself. Truly, I mean, they spend a great deal of time to do this. So, I mean, we can show that if we want to do the linear visco-elastic flows, I mean, we have a very simple model to do it. And when I say efficient, means if you counted flops and the way it evolves in a non-dimensional time, it's indeed very effective. I mean, it's easy to count that. And so can capture some phenomena in complex, not all, okay? And these need to be thought about. And much more to be done. As you know, this kind of model is, the LB model for hydrodynamics is for someone who does not understand hydrodynamics. And equally, the LB model for viscoelastics is for someone who does not understand viscoelasticity. So, I mean, much more need to be done. Anyway, any questions?
So the tail, people usually argue about the elongation of viscosity and birefringes tube, things like that. It'd be interesting to interpret your numerical results
Okay.
along those physical lines.
Jimmy, I mean, how do we interpret this? The way I see it is this, okay? Now, if I can derive some macroscopic equations, and I have certain consistency, numerical consistency, okay, convergence, then what I will do is that I will benchmark some of the non-dimensional parameters, okay, Deborah number or whatever number, then with some flow calculations. Once I do that, the question we really need to answer is that, can I do some predictions? Once I benchmark these parameters, can I take to another case to reproduce some of the phenomena you like to see? And if not, why? What is the physics we did not incorporate it? Or it's purely because of numerics is inadequate? There's two issues. So, for instance, I mean, I don't know if you know the recent result by Jay Shen, Ki Wan, Greg Forrest, they do a,
Film.
it's not film, it's a long drop and then becomes drop leads, that paper, okay? It's a very crude model, it's just a phase field model. And you can reproduce that. Think about it. What it takes to do, what we call non-Newtonian. And what aspect? There's just too many aspects of non-Newtonian fluids. It's a big elephant, I mean. So we do something very simple, naive, you might say, at the kinetic level.
So I have kind of general comment which relates to this, because what we're trying to do is a little like what was done with LB for liquid crystals.
No.
It is, because you're trying to put more information into the distribution functions or into the discrete Lattice Boltzmann dynamics
Mhm.
as a way of encoding physics beyond the Navier-Stokes equation. Right?
That part is true. But when you say liquid crystal, do you mean
Well,
the
well,
model by, for instance, Julia Yeoman's group and so on and so
For
forth?
instance, so just just to give you my viewpoint on it,
Mhm.
so they spent a lot of time developing, extra distribution functions and things within the LB scheme so that they could do liquid crystal hydrodynamics. What we found is that you can do that, but it's easier just to have an LB scheme with a forcing term, which is the liquid crystal stress, so that you have a Newtonian fluid, but with a stress field which depends on external order parameters. And then you evolve the order parameters with finite difference. And this is what we do now all the time.
Okay.
And so you're keeping the lattice Boltzmann for the momentum conservation and not trying to use it for anything additional. We've found that that's the most efficient way to proceed.
Okay. First of all, let me comment on the models you mentioned.
Mhm.
The model you mentioned rely on the following information. They already know what is the order parameter, and they
Oh,
already
yes.
know. Where did I use that?
No, I'm not saying you have a model of liquid crystals, you
No,
haven't, but you're
exactly.
trying
But
to
the key is that our picture is very caveman-like.
Mhm.
I only know the relaxation of certain mode. That's it.
Yes,
That,
Well-
but what they have is not.
I understand. But
So
what-
they already have the macroscopic
Yeah, yeah.
equation. That's the key.
Yes.
That's the distinction.
Right. But many people working in viscoelasticity also, in their mind, have a macroscopic constitutive equation, which they'd like to do numerically.
Mm-hmm.
And if you do what you're doing, which is to go in, at the level of the distribution functions and start putting in viscoelastic stuff, then obviously from that you can see what constitutive equation comes out. But if I say to you, well, actually I don't want a Jeffreys model, I want a Johnson-Sagelman fluid or
Mhm.
something, then it may take you some time to work out how to engineer that back into the discrete equations.
That is true. You see, the trouble with microscopic model is that if you have a very simple interaction, what usually comes out, it's far more than your macroscopics,
Mhm.
right? I mean, you can have a very simple relaxation, these kind, long rod type of fluid model. Well, what comes out is way more than Jeffrey or Maxwell or whatever. Well, are those things are correct? You only want to maintain the Jeffrey one, Maxwell one, and so on and so forth. If you want to do that, you have a heck of a hard time, like you just said.
Okay.
But if I don't
So
say,
it
wait a
depends on-
minute.
depends on what your target is.
Exactly. Okay, if you want to exactly solve the macroscopic equation, I don't want to do that.
Okay.
I'm trying to say that if you get a microscopic picture right, you can reproduce those phenomena with some extra terms.
Mhm.
And the key is how do we justify those extra terms? That's what we do. While the others do the other way around,
Yes,
as you
it's-
said.
It's a different philosophy.
It's macroscopic to begin with, all right, and have a finite difference equations. And they call Lattice Boltzmann, which is not.
Well, we call it hybrid. 'Cause we
Okay,
do
it's
the final
hybrid.
difference
Yeah,
on the-
exactly.
On the order parameter, and then we do use lattice Boltzmann.
Yes, for the hydrodynamics.
For the fluid.
And regarding the forcing term,
Yeah.
this way, long ago I predict, I said it's the same thing. But there are a group of people, as soon as they mention free energy, they entitled to the truth. And that's why they use that word. There's nothing else. If you don't use, free energy, you are an idiot. You're not supposed to be here. That's the way they see the word. And that's too bad.
Yes.
So there's a free energy with a kinetic formulation as well. So you can have a Boltzmann equation, you can use that word.
Exactly. But the key is that when you write down the equation is one thing, when you do the computing, it's quite another. How do you ensure you are preserving that free energy in the right way? And this has never been done properly. That's the trouble. So numerical analysis is usually the hard part, which nobody wants to do. The easy part is the color hydrodynamics.
If no one has another question, I have the usual after saying as a speaker. I have the usual Thursday after.